last lecture we have looked at hologram interferometry. By using a suitable optical arrangement, we can get the sum of principal stresses, that is sigma 1 plus sigma 2, which are known as isopatchics. If we use this technique in conjunction with photoelasticity, then we can get the individual principal stresses. Now, we will look at what are the steps in a double exposure hologram interferometry. Because I said vibration isolation is very important, and when you say vibration isolation is very important, you will have to know what are all the components in a general holographic recording, and we will have a look at it. We will also have a enlarged portion of it. Okay. So, what I have here is I have a light source, I have a next component as spatial filter. This spatial filter has a pinhole and also a lens. Then I have a beam splitter, then I have another lens, I have two mirrors, and I have a object to be recorded for the hologram, and I have a holographic plate. You need to sketch this, and we will see the optical diagram. What we will do is I will have to do two exposures. I will make exposure 1, I will also show exposure 2. So, you need to have a decent sketch of it. It will take you few minutes for you to do it. Take your time, because this is important, and I am going to show this in a slow motion, in the sense light travels at a very high speed. So, I am going to draw the diagram, and then I am going to show as if light moves, but it is at a very slow movement. And what I will do is I will make an exposure 1. Just look at what happens. Light comes, hits the beam splitter and goes to the mirror arrangement and comes to the hologram, and this is a reference beam, and from the beam splitter another set of rays go and illuminate the body, and this also comes to the hologram, and both happen simultaneously. For the purpose of understanding, I have shown how the reference beam falls on the hologram and how the light reflected from the object falls on the holographic plate. After you develop the holographic plate, it becomes a hologram. You can see the hologram. So, what you have here is you have the laser light source, you have a spatial filter, you have a beam splitter. So, beam splitter sends one set of beam to the hologram directly, holographic plate directly, you call that as a reference beam, and the necessity of a reference beam brings in the restriction of vibration isolation. If I do not require a reference beam, then I do not have to worry about vibration isolation. Because of the reference beam, I need to conduct experiment as carefully as possible. See, one of the requirement is even a normal running AC can alter the vibration characteristics. So, people keep the also AC away from the holographic table, they do not keep it near it. So, you have to take care of that, and I will repeat the exposure 1. You can just have a look at it, how the whole exposure takes place. So, you have a reference beam and you also have a beam reflected from the undeformed body. So, these two waves interfere and then I get this pattern. So, if I see this pattern, what I will see? I will see this 3-dimensional object. If I record this as a hologram, develop it and then reconstruct it, I will see the 3-dimensional object. And here I am not interested in knowing the metrology of the 3-dimensional object, I am not interested in the depth measurement or shape measurement of that object. I am interested because of loads applied, what is the deformation introduced in the model, that is what my interest. So, that is why you need a double exposure. So, what you do is in the first exposure you capture this. Now, what I do is, let me see whether I can do the second exposure. I have a button below, I will carefully press it. So, when I do the second exposure, you would have noticed I have not changed the reference beam, the body is deformed, and the deformation how I obtained I have not shown it in the figure. I have only shown that this is a deformed body. So, you have the light reflected from the deformed body is also recorded in the same hologram, same holographic plate. Now, when I develop this plate, I will be able to get the fringes which is representative of complete deformation of the 3-dimensional object. That is the advantage of holography, because you record so much information, interpretation becomes involved. Once you find it is involved, there are enough number of research students and research scientists across the world who try to crack this problem. So, that work is going on. To a large extent we have achieved. In certain issues you have to have certain complicated calculation, that is fine. And let us now repeat the exposure 2, then we will see the entire animation again. So, in the exposure 2 I have a reference beam that is not altered, I deform the body and I record another set of light rays on the holographic plate. And if we go in the sequence, we will see the exposure 1. So, only during exposure I have a reference beam which falls on the holographic plate, that is not disturbed when I go for the exposure 2. So, in between the exposure I have to deform the body. There are certain aspects that you will have to note down, how do you deform and what is it that you need to practice, all that we will see. Right now you look at the optical diagram and find out how the whole aspect is done. So, this illustrates that you have a reference beam and you have undeformed body, and then you have this second exposure. Second exposure is done where I have this light rays come from the deformed body. Now, we look at what are all the restrictions that you will have to look at when you are loading the model. See, the specimen is loaded and the second exposure is made, that you have well understood, and this is to be done what? This is to be done in darkness, total darkness, okay. And you have to ensure nothing of the optical arrangement can be disturbed between the exposures. So, it is not that you simply move your hand and then I mean disturb the alignment of any of the optical elements. This has to be done very carefully. So, that is what I have always been saying, experiments are planned and executed. It is not that you go quickly make some measurement and come and interpret the way you do it. Experiments have to be carefully planned. Also, you anticipate what is the type of result approximately. There may be error in judgment, but still you want to know the range, that is how you want to do the experiment. So, you can't disturb optical arrangement. And what are the other finer points? The object has to be mounted suitably so that it can be loaded without disturbing optical setup, and loading has to be done in dark. Even this you can practice. The other difficult point here is since you do not know a priori how the fringes are formed, you will have to have appropriate calculation to find out what is the extent of load that you should apply. And what is advised is you have to do rehearsal of the steps in applying the loads first in the light and then in darkness is decidable. So, you have to do some practice. So, when you want to record a hologram, you have to do this practice, and from loading point of view, since fringes will not be visible while applying the load, choice of suitable loads to generate sufficient fringes has to be calculated a priori or repeat the experiment until satisfactory results are obtained. So, you understand experiments are not that easy. it is back breaking. That is why people want to minimize the number of experiments that they want to do. The numerical simulation have to be looked at more in the light of reducing the number of experiments, because experiment is truth. Ultimately, any design that you want to release for the public, where any design deficiency can have serious consequences, you have to testify the results verified by experimental measurement. But experiments have to be done systematically, it takes time. Until you get satisfactory results, you may have to get it. This is where people found that why do you have to go and do this kind of double exposure. With advancements in computer technology, people are able to solve and address these issues reasonably well, and even now though there are restrictions, digital holography is also catching up. And what are the other things that you will have to look at? Because I said you are recording more information, reliable quantitative interpretation of holographic fringes is still difficult. There is no general method, but for specific applications interpretation is possible. See, one of the emphasis on many of these optical methods is people would like to minimize human intervention. What they want is they want to press the button and then finally say that this is the displacement, deformation, so on and so forth. In fact, I do not subscribe to that kind of a view. You need to use computers more for doing the routine job, but intelligence, human intelligence has to be used. Replacing human intelligence totally by any of the automated methods can result in absurd answers many times, and also the effort involved is quite high. Okay. So, what we find here is data interpretation is an issue, and what we will have to do is, when I want to do for specific applications, I said already the specific application is determining isopatchics. The optical setup should be adapted to the problem to simplify data interpretation. So, finally, what do you come down to? Planar surfaces are easier to handle. So, though you start with 3-dimensional surfaces, 3-dimensional displacement, I can record the information, but interpretation becomes difficult. But I will also say, when I have 3-dimensional information, it is very rich, and we will also see a separate lecture on how to extract as much information as possible by looking at fringe patterns alone. We will have a lecture on that. But once you come to any one of these experimental methods, the optical setup should be adapted to the problem to simplify data interpretation. A generic approach is still elusive and difficult, specific applications are possible, and you adapt the optical arrangement to simplify data interpretation. In this lecture, we have looked at the basic experimental arrangement in double exposure hologram interferometry. We have also looked at several restrictions while performing the experiment. Finally, we have discussed briefly the data interpretation in double exposure hologram interferometry. Thank you.